And here we go. This should be the last one. So we're going to do the same process again, solving for forces and motion, and then solving for impulse and momentum. All right, a car traveling at 30 meters per second forward strikes a barrier head on and bounces backwards. So we know it's an elastic collision. We start with two objects, they crash and they separate. So it's elastic. Backwards moving, backward is important, at 10 meters per second. So that is our final velocity. The driver is 100 kilograms. If the car was in contact with a barrier for only 0.5 seconds, how much force was applied to the driver during the collision? Show a solution using forces in motion and then impulse momentum. All right, so I'm going to do the same thing. I'm going to list out my givens right here in the middle so I don't have to do it twice. We know the final velocity. We know the initial velocity. So final velocity is 10 meters per second, right? No. Our final velocity is backwards 10 meters per second. Our initial velocity, we're moving forward, is 30 meters per second. That's the trick to the whole problem. That's it. If you don't catch that, you're going to struggle with this problem. So it's important to read all aspects of this problem and all problems. Take your time. Mass is 100 kilograms. How much force was applied to the driver? All right, so we only care about the driver. T is 0.5 seconds. It's kind of a long time for a collision to happen, but that's fine. Unknown, we're looking for force. All right, so to use forces and motion solution to find forces, we know we're going to use some variant of our net force equals mass times acceleration. But there's no acceleration given to us. Where can we get acceleration from? We can make a big jump and say that this acceleration is constant. It's absolutely not going to be constant in real life, but if we want to simplify this problem, we can say, okay, it's constant acceleration. Constant acceleration opens up those constant acceleration problems. So we have VF, we have V naught, we have T. We can use velocity as a function of time to get acceleration equals V naught plus AT. Solving for acceleration. We get acceleration equals VF minus V naught over T, which is delta V over T. Plugging in, we have negative 10 minus 30 divided by 0.5. And we would get, we're subtracting a positive from a negative, we're going to add a negative, so that's going to be negative 40 divided by 0.5. And we get our acceleration equal to 80, negative 80. Okay, so I can add in my acceleration equals negative 80. Now I can use acceleration equals F over m. Solving for force, we have force equals mass times acceleration. So we have negative 80 times our mass, which was 100. So our force equals negative 8,000 newtons, which just means it's 8,000 newtons applied to the driver from the front towards the back. Okay, so there's 8,000 newtons. Relatively easy if we made the simplification that the acceleration was constant. All right, so let's do this using impulse momentum. All right, so pretending we don't have acceleration and we didn't think about using acceleration because we've moved on, perhaps is the word, from these constant acceleration equations. Let's see. Impulse momentum theorem tells us that impulse, or your change in momentum, equals fat, F delta T. Not really fat because that's not an A, it's a delta. Equals J. Impulse, J. Let's see. We have a change in momentum, we have final velocity, and we have an initial velocity. What is our equation for momentum? Oh, it's been so long! Mass times velocity. And if it's delta, then it's delta V, so it's mvf minus mv naught equals F times delta T. Whatever you want to do right here is substitute, solve. You pick. I'm going to, you can even pull out the m's if you want. Just do whatever is going to be quickest for you. So, for me, explaining to you, I'm going to take a slightly longer way of explaining. So 100 times negative 10 minus 100 times 30 equals F times 0.5. Okay, so just be careful with your zeros. So we have negative 10 times 100, which will give us negative 1,000, minus 100 times 30, which is 3,000, equals F times 0.5. I'm going to divide each side by 0.5. Kind of save a step because I see I'm losing space here. Equals F. Negative 1,000 minus 3,000. We're subtracting a positive, so we're going to add a negative. So we get negative 4,000 divided by 0.5 to get our force. And when we plug that in the calculator, get out of the way, we get negative 8,000 newtons. That's it. Impulse momentum. I recognize that it's a collision by the phrase up here where it said it's bouncing backwards. So I realize that is a collision that are not sticking together. So that led me instantly to think, oh, I have a change in momentum here. If I have a change in momentum, I have the impulse momentum theorem at my disposal, because if I have a change in momentum and there's a force involved, how much force was applied, then I can use this equation. So that's it. Hopefully you're comfortable, but you probably are not. So do some practice. Seriously, do practice.